Hello, Calculus 12 students, and welcome to the Chapter 7, Lesson number 2 tutorial video. And in this tutorial video, I will go over first order separable differential equations. And in order to kind of get this topic started, I want to kind of start this video off with a very basic linear equation here. If I have if I have y plus 4 equals to 3, and if I ask you to solve this very basic linear equation, you can simply bring this 4 to the other side here, and you would get y equals to 3 minus 4, and your final answer here would be -1. So when you have a basic linear equation like this, you're likely to get, in this example, one solution, and your solution in this case will be a number. All right, so your solution is a number. It's a number because -1 is a number. So in this lesson, we'll focus more about something called differential equations. And a differential equation is something here on the right hand side. This right here is an example of a differential equation. It's a differential equation because it's an equation with a derivative, and here is my derivative expression right here. And when you're solving for a differential equation, you're not going to get a solution you're not going to get a number as a solution, but instead you will find your solution will be an equation. So basically, for a question like this, you need to find a function such that when you take its function and take its derivative, and if you add 4 to it, you'd get 3. Okay, so let me just kind of pause the video right here and write down some of the main facts that I've kind of stated so far. Okay, so welcome back to the video, and here are some of the key notes that I just kind of talked about before pausing the video. So this is a differential equation, and sometimes when you see the word differential equation, sometimes I'll use the letters DE for short. So it is an equation with a derivative. So when I say equation here, there's my equal sign, and my derivative right here is right there. And your solution is not a number, but the solution will be an equation. So for this kind of question right here, basically I'm asking you, can you find f of x, a function or an equation, such that when you take the derivative of that function, and if you add 4 to it, because we're adding 4 here, you're going to get 3. And since this is a very simple differential equation here, most of you can probably guess what f of x is, and just check your answer here. So I know a lot of students, when I went over this lesson in class, a lot of students guessed the answer to be f of x equals to -x. And what's the derivative of f of x? Well, it's going to be -1. All right, so if I take -1 and if I add 4 to it, do I get 3? And the answer is yes. So my solution in this case could be f of x equals to -x. This would be a possible solution to this differential equation right over here. Okay, so that's the difference between a differential equation and a simple linear equation, which is something you probably do in grade 8. Okay. Now, going back to this differential equation, I know some students can probably guess the answer here and guess that the answer is -x. In this lesson, we're going to be talking about how do we actually get -x without guessing and checking. Okay, so in order to kind of talk about the questions in this video here, let me just kind of solve this original problem here by giving you the proper steps so that we can find the answer of -x. Okay, so this is my original question right here, dy by dx plus 4 equals to 3. Now, when you're solving a differential equation, it's best to keep the numbers on one side of the equation here. So I'm just going to move this 4 to the other side, and you'll get -1 here. Now, we've been talking about derivatives before, and if you want to undo a derivative, you need to take its antiderivative. Right? Now, I've said in my classes that if we have other problems like u substitution questions where you have a du right here, if you have a du, then your integrand, which is the middle part, must be a function of u, right? You must have a u there if you have a du there. So before you can integrate anything, you want to make sure you have the same variables on You want to have the same variables before you can find the antiderivative. The problem is if I go ahead and take the antiderivative right now, I have a dy and a dx, right? So there's a problem there. There's two different variables there, so I can't take the antiderivative right away. What I need to do is I need to separate the variables. In order to separate the variables, I'm going to move this dx to the other side. So this will be dy equals to -1 times dx. All right, now I can take the antiderivative. All right, I can take the antiderivative because I have only one variable on each side of the equation, right? So the dy right here, that goes with the Superman sign. The dx goes with the Superman sign. So those things are like an item, okay? Now ask yourself, what is the antiderivative of dy? And if you're not sure what the antiderivative of this dy expression is, you really have this invisible 1 over here. So if you take the antiderivative of 1 dy, you just get y, right? And if you take the derivative of y, you get 1, right? So the antiderivative of dy has to be y. Okay, and that's going to equal to, okay, and then what is the antiderivative of this expression right here? So what's the antiderivative of -1? Well, that's going to be -x plus c. All right, and we have a plus c there because we have we have an indefinite integral. Before I move on, I know some students were asking in class, instead of just having a y, can you have y plus another constant, like another constant k here? And the answer is yes, technically you could have a constant, but if you take this constant and if you move it to the other side and combine it with that c, you just have another constant, right? So although you could have a constant for the y, when you combine it with the other constant on the right hand side, it doesn't really change anything. So a final answer here is going to be y equals to -x plus c. And just remember, if you do take the derivative of this, expression, you get -1. And if I take this -1, if I plug it back over here, -1 plus 4 gives you 3. Okay, and that's what this lesson is all about, is solving these differential equations. All right, now let's take a look at the very first, some of the rules, before we move on. The rules are you want to separate the variables. Okay, so make sure you have the same letters on one side of the equation. And sometimes all you really need to do is you need to look at your denominators. So in my example here, I have dx on the denominator and an f of y there. Sometimes all you really need to do is you just need to crisscross the denominators. And if you do that, you get f of y times dy equals to g of x times dx. And here's a little rule of thumb. Always have your dy's and your dx's at the very end of the equation. Okay, at the very end. Not at the front, but at the end. Okay, so notice that you have, once you've done that, you'll notice that you'll have the same variables on each side, and then you can take the antiderivative. So you want to integrate both sides, which is f of y times dy equals to the integral of g of x dx. Okay, so remember, the Superman sign and the dy's, they kind of come together as a pair, right? And you can take the antiderivative because all the variables do match up, right? They're the same variables. And after that, you just take its antiderivative, and the notation that I'll use to represent the actual antiderivative will be capital F of y equals to capital G of x plus c. Okay. Now, if you're not sure why I'm using these capital letters, I'm just trying to stay consistent with the notation that was presented in this course. So you may recall from the fundamental theorem of calculus, if I have the integral from a to b of f of x dx, I said that basically if you want to evaluate this kind of expression, you need to take the antiderivative of this guy, which we denoted as f of b, and minus that from f of a. So these capital letters here, the f expressions, those indicate that we have the antiderivative. So if I erase this, that's why I'm using these capital letters right here, because that just indicates that we have taken the antiderivative. Okay. And once we've done that, we just solve for y if necessary. Okay, and I'll come back to these rules once we kind of walk through a full example here. Okay, let's move on to question number 1 here. And for question number 1, I want to solve the differential equation, and I want to write the answer in the form y equals to f of x. Okay, so I need to find an equation here. Okay, and this part right here, y of 0 equals to 2, this is an initial condition. And from some of the lessons that we've done before, these, if you're given an initial condition, this will actually help you find your constant value. Okay, so if you're given an initial condition, your final answer should not have the constant. Okay, so when we do a differential equation, eventually you want to integrate both sides of the equation, but the problem is you can't do that right away because there's a y here and x there. There's different variables, right? There's an x there and a y there. I mean, the variables don't match up, so the very first thing that you need to do is, before you can find the antiderivative, you need to make sure that the variables are on the same side of the equation. And as mentioned in my previous example, sometimes all you need to do is you want to take the denominators and just crisscross them. Okay, so if I crisscross the denominators, I get 3y squared times dy equals to 8x times dx. And notice once again, my dy's and my dx's, they're at the very end of my equation. I don't have my dy in front, right? I don't have that. Make sure that the dy's and dx's are at the very end. Sorry. Okay, so once you've done that, the variables, all the y's are on one side of the equation, the x's are on one side of the equation. Now you can find the antiderivative, or you can integrate both sides. So integrate and antiderivative are the same, or pretty much the same thing. So I will integrate both sides of the equation. And if I do that, the question is, how do you find this antiderivative right here? Well, here's a 2. You just add 1 to the exponent, so you get y cubed divided by 3. And then you have the remaining red 3 there. And the Superman sign and the dy, the dy and the Superman sign, they go away because once you take the antiderivative, you're done. So the Superman sign, the dy, they just go away. This will equal to, well, what's the antiderivative of 8x dx? Well, that's going to be 8 times x to the power 2 divided by 4 plus c. Okay. And then before I continue here, let me just kind of simplify my expression here. This is going to be y cubed equals to 2x squared plus c. Okay. And I know that my initial condition was y of 0 equals to 2, right? That's my initial condition. Now, I recommend that you use the initial condition right away. Once you've found the antiderivative, use the initial condition right away so that you can find the actual value of c. Okay, so y of 0, that pretty much means x equals to 0, and this 2 means your y's are equal to 2. Okay, so y equals to 2, well, here's one y there, so if I plug in 2 there, that's going to be 2 to the power 3 equals to 2 times 1 squared plus c. Okay. Oh, sorry, I made a little mistake here. This is not 1, this is 0. Okay, sorry about that. Okay, if you do that, 2 cubed is going to be 8. That's going to be, this expression will be 0, and then c will have to equal to 8. Okay. So there it is. Let me just erase this now, and going back to, let me just kind of go back to this expression right here, highlighted in green there. If I go ahead and plug the initial condition in, I get y cubed. Sorry, I get y cubed equals to 2x squared plus 8. Okay, so there it is. I found my value of c. And if I go back to my notes here, the very last step is solve for y if necessary. Okay, so let's go ahead and solve for y. Here's the y variable, and I have this cube there, so if I want to solve for y, I just need to cube root each side. So this will be the cube root of 2x squared plus 8. Okay, so there is my solution to this simple differential equation. And just check to make sure that you follow the instructions here, and it says write the answer in the form y equals to f of x, and here it is. I do have my answer in the terms of y equals to something, so I'm good to go. Alright, let's move on with the next example here. For example number 2, solve the differential equation, write the answer in the form y equals to f of x, and once again here is my initial condition. And we will be using this initial condition once we've taken the antiderivative of both sides of the equation here. Okay, now when we have a problem like this, sometimes you do need to play with the variables and the expressions a little bit so that you can finally isolate the variables for one side of the equation here. So this one you may have to kind of play around with a little bit. This is x times dy by dx, and that's going to equal to y squared plus 4. Okay. What I'm going to do next is I have a dx here, and I'm going to move that to the other side. So this is going to be x times dy equals to y squared plus 4 times a dx. Okay, and then what I'm going to do now is I'm simply going to just exchange this expression right here and this expression over here. I'm just going to switch positions, and if I do that, I should get dy over y squared plus 4 equals to dx divided by x. Okay, so notice that my y variables are now they're all on one side of the equation, and my x variables are also on one side of the equation. Now, if you've done enough of these antiderivative problems, you'll recognize that you may want to rewrite these expressions as 1 over y squared plus 4 dy equals to 1 over x times dx. And one of the reasons why I'm writing my expressions in that format is because once I take the antiderivative, it's very easy to kind of find these kind of expressions on your formula sheets and find the proper antiderivative. Okay. Now this expression here on the left hand side, I mean this 4 right here, I can erase this 4 and put that as a 2 squared, and you'll notice that, is this a fraction? It is. Are the denominators written in powers of 2? They are, so you're probably dealing with an inverse trig function for the antiderivative. And if you look on your formula sheet, the antiderivative for this will be 1 over 2. It's actually the inverse of tan, which is 1 over 2, tan minus 1 over y divided by 2. Okay, and this 2 right here and that 2 right there, that corresponds with that 2 in the denominator right there. And if I want to find the antiderivative 1 over x dx, well, that's just going to be ln x, ln absolute value of x plus c. Okay. All right, let's go ahead and evaluate the initial condition here so I can find the value of c. My initial condition was f of 1 equals to 0, I believe. Yeah, f of 1 equals to 0. Just 1 second. Yeah, f of 1 equals to 0. So when I have this initial condition right here, whenever I have an x, I need to change that with a 1, and whenever I have a y, I need to change that with a 0. Okay, so let's plug that in. This will be 1 over 2 times tan inverse of 0 over 2 equals to ln of 1 plus c. Okay. Now the inverse of 0, I mean, this whole expression 0 over 2 is going to be 0, and since tan of 0 is 0, the inverse of that will also be 0. Okay, so for this expression right here, I know that the tan of 0, like when you have the function tan x, and when x equals to 0, your y value is 0, so the inverse of that will also be 0. And if you're not quite sure with that, please put that into a calculator, and you'll see that the inverse of tan of 0 is going to be 0. And if I have ln of 1, once again, that's also going to be a value of 0, because ln of 1 will be 0, and you can confirm that using your calculator, plus c. So then, therefore, c has to be equal to 0 there. Okay, let's go ahead and just erase some of this initial condition, and let me just kind of continue on with this part of the problem right here. Let me just kind of rewrite this. This will be 1 over 2 times tan inverse of 1 y over 2 equals to ln x, ln of absolute value of x, and then well, it is plus 0. I'll just leave it as plus 0 for now. And then finally, we need to isolate for y. In order to kind of finish off this problem, we want to write this in terms of y here. So let's get rid of this 2 here. So this will be tan inverse of y over 2 equals to 2 times ln x. And there's this blue is that corresponding to that denominator 2. And one more thing is, how do I get rid of this inverse tan here? Okay, so in order to get rid of that inverse tan, if you've kind of forgotten some of your basic trig rules, going back to maybe some of your pre-calc 10 courses, if you have tan theta equals to 3 over 5, if you had a problem like that, back in those days, I believe you were taking the inverse of each side. And basically tan inverse and tan, those would just kind of disappear, and you're left with theta, and theta would equal to tan inverse of 3 over 5, and you would just go to your calculator and put that in for some of your grade 10 courses. So going back to calculus 12 now, if I want to get rid of this inverse tan, all you have to do is just tan each side of the equation, and this tan, that inverse tan, will go away, and you're left with y over 2 equals to tan of all of this 2 times the ln absolute value of x, close the bracket. And if I want to get rid of this 2 there, I just kind of put a 2 in front of my tan expression, and then that should be it. So there it is. Here's my final answer to that problem. Is y equals to 2 tan y equals to 2 tan of 2 ln of x. Okay, so that was a good question, and let's move on with the next few examples here. Okay, for example number 3, this time, well, once again, I have another differential equation, but this time we have a trig function in here, and our initial condition has f of pi over 4 equals to -1. So for this kind of question, you're going to be you need to know some of your basic trig functions, and if you don't know the values of some of your basic trig functions and what the y and x values are, you may have to resort to your calculator. Okay. And another thing that you may recognize is that I have y prime now, so I don't have dy by dx, I'm using y prime. But the technique and the procedure is very similar. You want to keep the y's on one side of the equation here. So if I have y prime, I'll divide that by the y squared, and I'll get cos of 2x. Okay, so the procedure is still the same. And you get the y's on one side of the equation, and you get the x's on the other side of the equation. This expression right here, I'm going to rewrite as y to the power of -2 times y prime equals to cos of bracket 2x. Okay, and now let's take the antiderivative of each side of the equation here. And if I do that, things should be, whoops, sorry, I missed that one. So this would be the antiderivative over there. Okay, and once I do that, we can go ahead and find the antiderivatives of each side. So this expression right here, I can basically raise that to the power of 1. So this would be y to the power of -1 divided by -1 equals 2. Now what's the antiderivative of this expression right here? It's going to be, it's going to be 1/2 times sine of 2x plus c. Now, if you're not 100% sure on how I got this, you can definitely resort to your formula sheet. Because in your formula sheet, it does actually tell you the integral of cos of, I believe your formula sheet has in terms of k, so it might be kx. And basically the integral will be 1 over k times sine of kx plus c. Okay, so if you're not sure how I got this expression, I mean, just resort to your formula sheet, and there is the antiderivative of cos kx, in this case where k is 2. Okay. Alright, so once I've found my antiderivative right there, you want to use your initial condition, and my initial condition in this case was, let me just find my initial condition, it was f of pi over 4 equals to -1. So these questions are starting to kind of repeat themselves. We're just using different functions and different values. Alright, so let's go ahead and do this. If I have a -1, that means anytime I see a y, I plug in -1. So this is going to be -1 to the power of -1 divided by -1 equals to 1 over 2 sine of, okay, so if I plug in 2 times pi over 4 here, and just wait, you may not want to write this down just yet, but this expression right here, 2 times pi over 4, that's the same thing as just pi divided by 2. So this is going to be pi divided by 2. And if you do know your trig functions, sine of pi over 2, I believe, is going to give you a value of 1. Yeah, the value of sine pi over 2 is going to give you a value of 1. So if you remember your sine graph, this is pi right here, and this is pi over 2. So pi over 2 has a value of 1. So this whole expression right here is going to be 1. So this is going to be 1/2 plus c, because I saw that 1/2 right there. And if I go ahead and evaluate all of this, well, that's just going to give me a positive 1 because I have 2 negative signs there. So in this case right here, sine is going to equal to, just one second here. If I just bring the 1/2 to the other side, I should get 1 minus 1/2 equals to 1/2. So c equals to 1/2 after I do all the algebra there. Okay, and now I'm going to go ahead and just erase some of that, and let's go ahead and work from this equation right here. If I bring that up here, I think this is going to be -1 over y, equals to 1 over 2 sine bracket 2x plus 1/2. Okay, so I just kind of rewrote the rewrote the left hand side as just negative 1 over y, just to kind of help me isolate for y. If I want to get rid of the negative sign there, this will be 1 over y equals to negative 1 over 2 sine bracket 2x minus 1/2. And then if I have 1 over y, I can just flip everything. Okay, so let's just flip everything. This will give me y equals to 1 all over negative 1 over 2 sine of bracket 2x minus 1/2. And I will leave my answer like this. I mean, obviously you can simplify this a little bit more, but since I don't want to spend any more time doing this problem, I'll leave the final answer like that. Okay, let's move on. We have a few more examples to kind of go through before we finish this tutorial video here. Okay, so example number 4, another one, solve the differential equation. So now that we've seen a few examples of differential equations, you should be very comfortable with. You should start to feel more comfortable with the general approach with solving differential equations. I have a y here and a y there, and I have a dx here and x cubed over here. So this is going to be dy divided by the y equals to 4x cubed times dx. And before I continue here, I'm just going to rewrite this expression over here as 1 over y times dy. And the reason why I'm rewriting the expression like that is because once I take its antiderivative, once I integrate that side of the equation, I know exactly what the antiderivative will be. And this will be 4x cubed times dx. Alright, so let's go ahead and find the antiderivative now, the Superman signs. And this expression right here, I mean 1 over y, I know what the antiderivative of that is. That's just the ln of absolute value y equals to, well, I just take this cube here, raise that to the power of, add 1 to that, so that should be x to the power 4 divided by 4, and then I have the coefficient of 4 in front, and then you'll notice that the 4's here will just cancel, so then you just have x to the power 4 plus c. And my initial condition here is y of 1 equals to 3e. Okay, all right, so let's go ahead and plug in the initial conditions now. This will be ln absolute value of 3e, close the bracket there, to the power of, equals to 1 to the power of 4 plus c. All right, well, 1 to the power of 4 is going to be 1, and the plus c, I'll bring that over. This expression right here, ln 3e. Now, you might have to go back to some of your log properties. I know that the log of AB, where a and b, they can be constants or variables. That's the same thing as log a plus log b. So let's go ahead and use log and ln. The rules are the same. So if I go ahead and if I expand this guy right here, this is going to be ln 3 plus ln e. Okay, and you may remember that ln of e, that if you put that in your calculator, ln of e that will be 1 equals to 1 plus c, and this will be ln 3. And if I add up all the terms here, I know that c will equal to ln 3. Okay, so you can actually do this question without using your calculator if you do remember your ln properties. Okay, let's just go back now and continue this equation here. Let me just start back from this part of the equation now. If I just carry on with this part of the problem here, I get ln of absolute value y equals to x to the power 4 plus ln 3. Okay, now how do you get rid of this ln here? Because the idea is you want to isolate for this blue y, right? Now, if you don't remember your e properties, you can raise everything to the power of e. So if I have a question like log x equals to, I don't know, 5x plus 2, and if I want to solve for this x right here, I can raise everything to the power of 10. Alright, if I do that, I get x equals to 10 to the power of 5x plus 2, for example. Okay, so if I have ln absolute value y equals x to the power 4 plus ln 3, I can raise everything to the power of e. And if I do that, that goes away, and I'm left with the absolute value y. And since I'm dealing with an exponential function here, I can get rid of the absolute values because this will be a positive above the x-axis, and this will be e to the power of x to the power of 4 plus ln 3. Okay, so this right here, I will give you full points for an answer like that. Textbooks may not have the answer like this because you can simplify this a little bit more. If you go back and use some of your basic exponential properties here, if I have x to the a times x to the power b, this is the same thing as x to the power a plus b. So if I'm given this expression right here, I can go back and write this in terms of x to the power a times x to the power b. And if I go ahead and expand this, this will be x to the power of x to the power 4, y equals to e to the power of x to the power 4 times e to the power of ln 3. And right away, I know this e and that ln, they will cancel off, so I'm just left with this 3 here. And if you do put this whole expression to your calculator, you are just left with 3. And then just bring down the e to the power of x to the 4, and that's more of a simplified answer to this kind of a problem. Okay, so based on those 4 examples, I mean, some of these problems are a little bit lengthy here, but that's how you approach these differential equations. For Calculus 12, we have these other word problems. When we're dealing with the differential equations part of Chapter 7, we do have some word problems that go along with for this part of the chapter. And the kind of word problems that do kind of come up, we have these exponential growth and decay problems. They're very similar to some of the word problems that you may have seen pre-Calculus 12, where you're dealing with like half-life or double time, those kind of problems with radioactive substances, and we do have those kind of problems in Chapter 7 as well. So before we kind of get into those kind of word problems, let's consider one more differential equation here. If I have dy by dx equals to ky, where k is just a constant, right? K is a constant like the number 2 or 5 or 10. How can we kind of solve like a differential equation like this? Well, we take the same approach here. I mean, here's a y here, and here's the dx's. Let's kind of separate the variables here. So this is dy all over y equals to k times dx. Okay, and I'm going to rewrite this as 1 over y times dy equals to k times dx. And let's go ahead and find the antiderivative of each side. And if I do that, I get ln absolute value of y equals to kx plus c, right? This is an indefinite integral, so I need my constant there. Then let's go ahead and raise everything to the power of e here. So if I do that, I get y because this part just cancels off, and this is an exponential function, so I can get rid of the absolute value signs. So this will be e to the power of kx plus c. And we saw this, if I go ahead and expand this, this will be e to the kx times e to the c, and this e to the c is just basically, that's a constant, right? That's just a constant. So if I want to kind of rewrite this using simple notation, my final answer would be y equals to maybe the letter a times e to the kx, where this letter a right here, that's just a constant. Okay, so instead of writing this e to the c here, I mean, we can just kind of use the letter a and just say that we have a constant right there. And this is the kind of problem that will, this is the kind of the solution to this kind of a differential equation, and we'll be using this solution to kind of approach some of the word problems in this chapter as well. Okay, let's move on to the final problem in this lesson video here. I have this exponential growth and decay modeling example. So in this problem, I have a radioactive substance, and it decays at a rate proportional to the amount of substance present, and is modeled by the differential equation dy over dx equals to ky. And I do apologize, there is a mistake in this equation right here. Can you please change this to dy over dt equals to ky? Okay, so in this problem, they do give you this differential equation here, and then they want to find out how long will it take for 200 grams of this substance to decay to 1 gram. Okay, so this 200 grams right here, this is kind of like your initial amount, and this 1 gram here, that's your final amount. Okay. And I guess this question has to do with time, right? So your initial amount is, this is when your time is going to be equal to 0. That's your initial time, right? Because at the beginning your time should be 0. And then after some time, I don't know how long, it might be a few years, we want to know how many years will it take for us to get to go from 200 grams down to 1 gram. So we want to find, we need to find the final time in a problem like this. Okay, and this question should be very similar to some of the kind of problems that you've seen in your pre-calculus 12 class. Okay, so if I have my differential equation, which is dy over dt equals to ky, in order to kind of start this problem, let's start with the differential equation here and let's solve this. Let's get the dy's all on one side, or the y's on one side, and this is very similar to the problem I just did above here. This is k times dt. And if I go ahead and if I integrate both sides of the equation here, this part right here, I should get ln absolute value y equals to kt plus c. Now hopefully this t is, sorry, let me just rewrite this. Hopefully this t right here in yellow, hopefully that's okay because I'm taking the antiderivative with respect to time here, so it's kt plus c. And if I e both sides of the equation now, this will be y equals to e to the kt. And I'm going to go ahead and just do this right away. This c means I have a constant in front. Okay, so this is my solution to my differential equation here. Y equals to ae to the kt. Okay, now if I look at my initial amount here, the initial conditions here. Let's move this down here. I know I have 200 grams. All right, so that means y is equal to 200 grams. And my time is going to be equal to 0. So at the beginning I have 200 grams. So if I plug that into my my solution here, a e to the kt, I know that y is going to be 200 grams equals to a, which I don't know, e to the k. Do I know k right now? I don't know what k is either, but I know that time is going to be 0. Right? So I know time here is going to be 0. Okay, so this is the same thing as 200 equals to a e to the power 0, so this means this e to the power 0, that's going to be 1, so this will be a equals to 200. Okay, so before I can solve the problem, we need to go ahead and find what this value of a is. Alright, once we find the value of a, we also need to find the value of k afterwards, and then we can find the final value of y, because we know y is going to be 1, and then we can find out how long it will take, which is the value of t. Okay, so let's go ahead and rewrite this into our problem now. This is going to be y equals to 200 e to the kt. Okay. Alright, so before we can find, remember our goal is I want to find the final time, right? I want to find out what this time is. I know I found my a value now, but now I also need to find this value of k there, okay? So before we can find time, let's go ahead and find k. And in order to find k, we need to use this half-life problem here. Okay, so I realize in this problem there's another, actually, you know what, I'm gonna have to stop the video right now because I realize there's a few actually, you know what, I realize that we can't solve for k here because I forgot one more piece of information. Can you please write down in the problem, I do apologize for this, my bad, can you please write down that we have a half-life of 90 years? And I'll try my best to go over this example in class again, but I realized that this problem had a few typos and some missing pieces of information. I realized if we're not given this half-life of 90 years, it's actually impossible to find the value k. Okay, so half-life is 90 years. Okay, so what that means is if t is going to be 90 years, and if we're initially given 200 grams at the beginning, the half-life or the remainder should be y equals to 100. Now 100 is half of 200, right? So initially when time equals to 0, we start off with 200 grams, and if the half-life is 90 years, that means after 90 years we should have 100 grams. So if we use t equals to 90 and y equals to 100, then I can find the value of k. Alright, so y is going to be 100. 200 remains, e to the k times 90, and then we need to solve for this k value here. So let's take our 200 and the 100, divide those. So this will be 100 divided by 200 equals e to the 90k. this will be 1/2 equals to e to the 90k. And then I can ln both sides of the equation here, ln that. So this will be ln of 1/2 equals to 90k. Divide each sides of the equation by 90. So once I'm done, k would equal to ln of, I'll say 1/2 divided by 90. Okay. All right. So now if I go back and to my original problem now. Just 1 second here. I know that I know y equals to 200 e to the ln of 1/2 over 90 times the time. Now I can go back and solve for my original. I can go back and solve for the missing unknowns. And for this kind of problem, I want to know how long will it take for 200 grams of this substance to decay to 1 gram. All right. So how long will it take for this y value to reach a value of 1 gram? So let's just change this to a 1 now, and that's going to equal to 200 e to the, oh boy, ln of 1/2 over 90 times the time. And once I solve for time here, then I've pretty much solved the problem here. Okay, so in order to do this, you divide both sides of the equation by 200, so this will be 1 over 200 equals to e to the ln of 1/2 over 90 times t. Okay, and then I can ln both sides of the equation here. If I do that, I get ln of bracket 1 over 200 equals to, now I'm left with, well, this ln and that e, they will just kind of go away. And now I'm left with ln of 1/2 over 90 times t. Okay, and then I can move the 90 above, so this could be a 90 over there, and then I can erase that, and then I can take this whole expression and divide it by ln of 1/2. So ln 1/2, divide that by ln of 1/2. These guys will cancel, leaving you with t. And if you put that into your calculator there, you should get about 687.95 years. Okay, so I apologize that this last example was a bit sloppy. I will try my best to go over this example one more time in class, but I think you have enough tools to start the differential equations homework assignments now. All right, thank you very much. Bye.